Hi. In Lab 5, Part 1, you're going to be looking at a video of a magnetic leve track. And on that track, you're going to see a magnetic disc that's been supercooled, and it is going to float up and down this track. And what you're going to do is it's going to start at a height, and it's going to go up. Given the initial velocity that it has, it's going to go up a certain height. And you're going to predict how high it will go. So the reason we're looking at this type of track is this is a situation where there's very little friction in the system. And because of that, none of the mechanical energy, or very little of it, is going to be turning into friction or heat energy. So that means that all of the mechanical energy will be conserved. So to start with, it's going to have a lot of kinetic energy, and then it's going to have, as it loses its speed, all of that kinetic energy is going to be converted to potential energy as it rises in height. So if it had 100 joules of kinetic energy, then it would rise to the height necessary to have 100 joules of potential energy. So think about it this way. If you were riding a roller coaster, as the roller coaster goes up the hill, it gains potential energy, but as it goes down the hill, it loses height and it gains kinetic energy. If there's no friction in the system, then as it goes up the hill, where it has all of its potential energy, all of that energy, as it goes down the hill, gets turned completely into kinetic energy if there's no friction in the system. And then as it goes up, the next hill, if it's moving, it still has kinetic energy, but it also has potential energy. And if you add those together, that should be equal to the sum at the top of the first hill of the potential energy it had when it wasn't moving at all. So, and this is assuming there's no friction in the system. Now, in a real roller coaster, there is friction. And that is why the first hill is always the highest, because you can never have enough total mechanical energy once it starts moving, because some of that mechanical energy gets turned into heat energy. So you'll never be able to get up to the same height that you started at, because you'll never have enough mechanical energy equivalent to that potential energy to start with. Some of it turns into heat energy. Can't really recoup that back into kinetic or potential energy easily. So in this lab, you're just going to look at a system where there's very little friction so that you can make a prediction. So you're going to use the video analysis tools here to determine the speed that this puck has when it's traveling in a straight line. So you know, that's pretty easy, right? I mean, there's lots of ways that you can do it. You can make a graph of distance versus time and take the slope of it as it's, right here before it starts to go up. That will give you the speed of it. You could measure the distance that it travels and the time that it travels and find the average velocity that it has right before it starts to go up. And that can be used to determine its kinetic energy to start with. And that can be set equal to the potential energy it'll have when it rises to its highest point. So the kinetic energy is what you want to calculate, but you're going to have to do it by making some measurements in the video and using video analysis. Then you're going to set that kinetic energy equal to the potential energy it's going to have at the maximum height, noting that the mass will cancel out, so you don't need to know the mass of the puck. You just need to know that gravity is 9.8 meters per second squared, and then you can use that equation to estimate the height that it will rise. And then you get to verify it and see if you're right.